resume recording, and let's talk about some math. So you might have noticed that I keep using Riemannian metrics in this course, even though this isn't sort of strictly a Riemannian geometry class. I just noticed right before class that someone had posted a question about whether we really needed to use Riemannian metrics in the notion. I mean, I think the answer is yeah. I mean, it's maybe you could get away with doing some of this stuff without ever picking a Riemannian metric, but it makes your life a lot harder if you're never willing to do that. It's a little funny because sometimes you just have to choose one and it makes no difference what it is. But that's how it goes sometimes. But there's actually a closer connection between Riemannian and symplectic geometry than that answer would suggest. And that's kind of tied up in our subject for today, which is about almost complex structures. So, right, manifolds can have additional structures. We've talked about symplectic ones. I've assumed that you're at least familiar with the existence of Riemannian ones and the definition, even if you don't really know anything about Riemannian geometry. And there's sort of a third partner there in that trinity, which is complex structures. And so today we're going to talk about, I should say, almost complex structures, how they relate to symplectic things and implicitly thus Riemannian things. All right. Somehow, like once you've talked about Riemannian structures and symplectic structures, you're kind of forced to also think about almost complex structures. And they actually play a pretty important role in a lot of modern symplectic geometry. So I think that's definitely something we should suggest. All right. So what is complex geometry? I'm not assuming you know anything about it other than like what the complex numbers are and how complex vector spaces work. But yeah, so there's a certain amount of, you can probably kind of guess, right? So with both Riemannian and symplectic geometry, we've talked about a basic structure on vector spaces, either having an inner product or having an anti-symmetric bilinear form, and said, oh, well, what would happen if you had a manifold and you put that structure on all of the tangent spaces in a consistent sort of smooth way? So almost complex structures are exactly the same thing, but the structure you're putting on the tangent spaces is that of being a complex vector space of half the dimension. So let's just talk about this on the vector space level first. So if I have an R vector space, this is one of the things that kind of gets confusing here is like, right, we've been talking about differential geometry. So kind of the base field for everything is R. And now I'm bringing in complex numbers, but I'm starting with an R vector space and then saying a complex structure on a real vector space is a real linear map whose square is minus the identity. Now, having such a map, I can define a module structure over the complex numbers by letting the complex number I act by this J. And so I've made my V, the same underlying abelian group, into a complex vector space. This is one of these things that like, it's really very simple, but it like can be a little hard to kind of wrap your mind around that. I mean, if you have a complex vector space, you can just forget about how I acts and get a real vector space twice as large. Now I'm talking about undoing that operation, which there isn't just one way to do. It's an extra choice of structure to do that. All right. And we call a complex structure on a vector space compatible with a symplectic structure on that vector space if, when we put them together, so we take the symplectic structure, which is an anti-symmetric, non-degenerate bilinear form, and apply it to U j times V, Well, that gets us another bilinear form. It's not obviously symmetric or anti-symmetric. It's just its own thing. But sometimes that will be an inner product. So we call the complex structure and the symplectic structure compatible if it happens that that bilinear form is an inner product. So non-degenerate and positive definite. If we look at what that means that when I apply my symplectic form to hitting U and V with the complex, with this complex structure map J, that's the same as my original symplectic evaluation on those guys, right? So I use the definition to turn it into the inner product. I use the symmetry of the inner product. I use the fact that J squared is -1 in this next line. Oh, I'm sorry, there's, oh no, that's right. Yes, good, yeah. Using the fact that J is -1, and then I use the anti-symmetry of the symplectic form again. All right, and then I also have to have positive definiteness. So this is sort of, right, this complex structure. If you think about what happens when you try to diagonalize a matrix over the reals, whose square is -1, it kind of has to have this structure of having two-dimensional planes where it's acting like on the complex numbers, where it's acting by rotation a quarter way around. And what we're saying is that plane has to be symplectic, and it has to inherit the right orientation from the symplectic structure. Right, that I have to get something positive instead of something negative. One of the things, I'll talk about this a little more later, right? A symplectic form on a vector space gives you an orientation on any symplectic subspace, so in particular a two-dimensional one, and a complex structure on a two-dimensional real vector space also gives you a preferred orientation, right? And you want those to match. That's what this condition is. For whatever reason, this is called tameness. All right, so the kind of picture you should have is there's this kind of triangle of complex, symplectic, and Riemannian, and having two of these structures will tell you something about the third. I wish I could just say, oh, if you have two of them, then you have the third. It's not quite that simple, but that's kind of the cartoon you should have in your head. And maybe one note here, one of the reasons that Riemannian metrics are so useful is they always exist. So every real vector space has an inner product. Every manifold has a Riemannian metric. But both symplectic and complex structures come with restrictions. They don't always exist. So in a vector space, they have to be even dimensional, right? If you have a complex vector space and you think about it as a real one, its real dimension is going to be twice its complex dimension. So it has to be even dimensional. And we've already established that symplectic things have to be even dimensional. All right. Any questions? So this is mostly just kind of wrapping your head around how we're talking about complex structures on real vector spaces. One way to think about this triangle is that having compatible complex and symplectic structures always gives you an inner product. In fact, an inner product and a complex structure always give you a symplectic structure, basically undoing the formula that we had before. So this is part of what I mean about like, oh, well, you have this nice triangle. If you have two sides of the triangle, it's not quite true that you always get the third, but there's a relationship there, right? There's an actual compatibility you need between complex and symplectic structures to get a Riemannian metric. Oh, and actually I lied here. I was not thinking. Sorry, this is only correct if this complex structure is anti-symmetric with respect to the inner product. Sorry about that. I think I was just kind of writing in my notes and didn't think carefully as I should have. But right, for this omega to be anti-symmetric, I exactly need that J is anti-symmetric as a matrix with respect to an orthonormal basis with respect to this inner product. All right, so again, you need some compatibility between the inner product and the complex structure, and then you'll get a symplectic thing. All right, so there's sort of a third side of that triangle, which is what happens if we have an inner product and a symplectic structure. Okay. Is there a way to combine those to get a complex structure? And the answer is yes, but it's a little bit tricky. So, of course, you might hope that you could just take this symplectic structure and define J by using those formulas above, right? Seems like a promising idea. And indeed, that gives you a well-defined map. I'm going to follow Candace de Silva, and for whatever reason, she switches where she puts the map. So this map A, it's instead of being on the second thing in the symplectic form, it's on the first thing in the inner product. It all works out okay, but for whatever reason, it's better to take that map. But the point is, you can sort of look at that formula and try to define a complex structure, but just as we needed a compatibility between the complex and symplectic structures to get an inner product, and a compatibility between the complex structure and the inner product to get a symplectic thing, there's no reason that this guy A has to satisfy that A squared is equal to -1. So what is true is that this guy is skew symmetric, anti-symmetric. Applying essentially the same argument from before, we find that when we take its adjoint, we get -A. All right, so what does that actually mean? Well, if I have a skew symmetric matrix, you can look at its characteristic polynomial, and all the roots of the characteristic polynomial will be imaginary. And this guy A is invertible, so all its eigenvalues are non-zero. So I'm getting non-zero imaginary numbers, which of course come in conjugate pairs. So I'm going to have eigenvalues sigma 1 plus or minus times I, sigma 2 plus or minus times I, sigma n plus or minus times I. And I could diagonalize all the way down to a diagonal matrix with those entries over the complex numbers, but of course I can't do that over the reals because they're not real numbers. So the closest I can get is to find an orthonormal basis where I have this structure. So I have, instead of a diagonal matrix, I have these diagonal blocks. And this is some basic linear algebra. I think I wrote a comment about this, right? So you'll find that you can look at the minimal polynomial of this matrix. It's a product of terms of the form x squared plus sigma I squared. And so you can break your, you can go and look at the proof of the sort of generalization of Jordan decomposition for fields that aren't algebraically closed. And what you're going to find is that your vector space is going to be the sum of the kernels of a squared plus sigma I squared, right? So if that's the product, right? This is the product of a plus sigma I times I, a minus sigma I times I. So the kernels of these factors would be the sigma I, sigma 1 times I minus sigma 1 times I eigenspaces. When I take the product, I get something that's defined over the reals, but whose kernel is going to be the sum of those two eigenspaces. So I'm kind of picking up those two eigenspaces. If I pick something in that kernel, then V and AV are linearly independent, and V and 1 over sigma I times AV are both have the same length. So those give me kind of the first two vectors of this form, and then I can take the perp to those and keep going. All right. I just write this out because if you read Canis Silva, she kind of just does this as all abstract linear algebra, and at least I read it and I have no idea what's going on, right? I mean, if you kind of already understand polar decomposition, then fine. Like all I'm doing is explaining to you the polar decomposition of an antisymmetric matrix, but I at least like thinking of it this way. So we have these annoying sigma i's, and there's this matrix that kind of plays a key role in polar decomposition, which is A times A star. But if you look at this formula here, A times A star, that's just the diagonal matrix whose entries are sigma 1 squared, sigma 1 squared, sigma 2 squared, sigma 2 squared, etc., all the way down. The square root of that is just strip off all of those squares. You get sigma 1, sigma 1, sigma 2, sigma 2. Yes. And note here, I assumed that my sigma I was positive. So here I'm taking a square. I would get the same answer whether I had sigma I or minus sigma I, but it actually matters when I take the square root that I mean, oh, I have something where the diagonal entries are positive, take the positive square root. All right. So this polar decomposition, which Canis Silva uses, it's a canonical way of factoring any matrix into something which is positive definite and unitary. You know what I mean? Yeah, I think that's right. And of course, if I look at what happened in coordinates and the coordinates I had above, I'm now getting J is, well, exactly sort of the thing I would look for as a complex structure. 1 minus 1, 1 minus 1, etc. Okay, so I'm exactly getting rid of those sigma i's.
It looks like maybe you have like either your expression for J is like the square root is on the wrong side, or the expression for A, the square roots are on the wrong side.
The star was on the wrong side. I don't know if that actually matters. Maybe it does. Sorry, what do you mean the square root's on the wrong side?
I mean, maybe it's right, but I was just kind of putting these two together. I don't see the square, like I would think that the inverse and the not inverse square root cancel each other out, but then you have an A in the middle. Maybe the A just can move through.
The inverse and the not inverse. So
just because it's matrix multiplication. So does it matter which side we're multiplying on?
Oh,
they're
it
diagonal
actually doesn't.
matrices.
It doesn't. These guys actually commute.
Oh, okay.
They're diagonal.
Oh, yeah.
Well, J isn't diagonal.
Yeah, but the square root of A star is diagonal. So it.
Yeah, I mean, if you look at the actual matrix, right, J is block diagonal, and on the corresponding block, this guy is a multiple.
Okay, that's why.
So it commutes. And I mean, this is a general fact about polar decomposition, that it's sort of that the two things you pull out commute with each other. All right, so yeah, if that sort of realized that when I got there, but yes. And that's pointed out in Canvas so that they can be, so you can write them in either way. And you can check that explicitly on these matrices that you multiply on either side. Either way, you're just getting rid of the sameness. All right. So looking at this matrix, it's obvious that its square is -1. You can also check that in a coordinate-free way, using the fact that J is orthogonal and skew symmetric. So, right, because I'm orthogonal, J inverse is J star. And then by skew symmetry, that's -J. All right. But note here, one thing that's worth noting. So we put in a symplectic structure and a inner product, and out we got a canonical choice of complex structure. It's compatible with our original symplectic structure, but it doesn't give me the original inner product back. So if I sort of take this symplectic structure and this complex structure, and I want to check if they're compatible, I should put J in here, and I should see if what comes out at the end is an inner product. And it is, because I have my original G, and I put in a positive, definite, and symmetric matrix here, right? It's actually a diagonal matrix in the basis I chose, but it has positive entries along the diagonal. So this guy here is still an inner product. Candice De Silva does a much more complicated calculation where she checks this other version of the properties here. Checks this tameness, and she calls this symplectomorphism. Okay. All right, and I know this is kind of a weird operation, so I wanted to kind of think a little more intuitively about it. So if I'm two-dimensional, then a symplectic form is a volume form, right? It's the top form on my vector space. And so it's something that, right? When I take omega of uv, what I'm doing is I'm taking the signed area of the parallelogram u, v, u. All right. So, I mean, if I take the standard symplectic form, it's really like area in the standard sense. But since we're kind of trying to think about things in an abstract way, I'm saying this is like the definition of the area of this parallelogram, right? Don't assume you have a metric. So don't assume you have some other way of defining area. I'm just telling you what area is. All right, but on the other hand, if I also choose a metric, I'll get another notion of area, right? I'll get a notion of, so G tells me I can look at two orthogonal unit vectors. Yeah, maybe because I didn't prepare this. Being a little bad, but I'm writing the wrong thing. So G allows us to define E1 and E2 orthogonal unit vectors. And so I get a notion of what a unit square is. And I can then go to the symplectic form and look at what the volume of this unit square is with respect to the volume defined by the symplectic form. And if I just choose my metric in my symplectic form totally randomly, then there's going to be no relationship between those numbers. That number could be anything, right? And so exactly the reason we have to stick in this guy square root of a star is that this guy a star, hopefully I did this calculation right, I think that's right, is going to be multiplication by the volume of the unit square as defined by the symplectic form, right? So I can take this unit square, its area is some number A. And so exactly what this proof is telling me to do is, oh, you should scale your metric by this, this number A, and then you will get the volume according to the metric and the volume according to the symplectic form to line up. I'll also note here, right, this unit square, it doesn't have a preferred orientation, right? So at the end of the day, what I end up choosing, so J ends up having to send E1 maps to E2 if the symplectic form E1, E2 is positive, I think, and E1 to minus E2. This is negative. So if I only have a metric, I have this square, but I don't have an orientation on it. So its volume doesn't pick up a sign. But the symplectic form and the complex structure both have to induce an orientation, and I want to make sure those orientations are the same. So if you sort of find this proof a little confounding, I think it's worth going through this sort of simple example, seeing if I made a dumb mistake in here, since I think this is almost surely right. But yeah. The reason that that's right is this tameness condition is exactly that VU is positive, right? So if this signed area with E1, E2 is negative, I made the wrong choice of which one was E1 and which one is E2. And I have to send E1 to minus E2 under my complex structure instead. All right, and the proof up above is basically, well, by linear algebra magic, when I have a complex structure, when I have an inner product and a symplectic form, there's sort of a canonical way to choose these planes, and I do this operation on each one of the planes, right? If you look at what happens in here, right, looking at the eigenvalues of A squared gives me the separation into subspaces. Okay, maybe it's not necessarily planes if the same eigenvalue comes up twice, but I certainly get a decomposition into two-dimensional subspaces. And I'm doing this operation of saying, okay, the complex structure should send a unit vector to a unit vector, and the symplectic form tells me what the orientation is. And I should maybe say, like, I definitely had a moment reading through Canis de Silva where I said, man, this So it's really getting kind of elaborate when, like, it's not very hard to prove that even dimensional real vector spaces have complex structures, and it's not all that hard to prove that if you have a symplectic form, you can come up with a compatible complex structure, basically by choosing a standard basis. And I think Candace Silva even writes this down. You choose a standard basis, and like you choose your complex structure to send E1 to F1 and E2 to F2, etc. And F1 to minus E. But the reason to do it like this is if we're going to be doing stuff about you have one of these structures on every tangent space, and you want to do these you want an operation you can do in a kind of consistent family way, right? And anything that involves choosing a standard basis for the symplectic form, there's no obvious way to do in a family. So if I have a symplectic form, I can't like globally choose a basis of the tangent space of all tangent spaces simultaneously, which has these standard basis properties. That would require the tangent bundle to be trivial as a vector bundle. So I want to avoid doing that if I can. And this is a nice way to avoid doing that, to make it clear. Yeah. So we'll talk about that later. It'll be kind of clear why this is a good thing to do. All right, any questions about this linear algebra portion of things? Okay, so as I say, we now want to think about, well, what happens if we do this simultaneously on all the tangent spaces of a manifold? So an almost complex structure on a manifold means a consistent family of complex structures on the individual tangent spaces. So for every point in the manifold, I have a complex structure, a R linear map whose square is minus the identity, that varies smoothly with respect to P. So it's a map of bundles from the tangent bundle to itself, whose square is minus the identity. You might notice there's this annoying thing, almost, right? Why didn't I just say a complex structure is a structure in a manifold, yada, yada, yada. And the reason is, by kind of analogy, right? When I have a symplectic form, it's not enough to have a symplectic structure on all the tangent spaces. I also want the corresponding two form to be closed. So the issue with the almost here is I haven't told you what the right condition, that's sort of an analog of the symplectic form being closed is. We'll talk about this in greater detail on Wednesday. The point is a complex structure is reserved for one of these that really looks locally like the complex structure on Cn, right? So when we looked at symplectic forms, you needed this closedness condition to have the Darboux theorem hold, to have that you locally have coordinates that make you look like the standard symplectic structure on the cotangent bundle of Rn. However, let me just sort of put the very motivating example, which actually will be a complex manifold, not just an almost complex one, which is if I have a holomorphic map from Cn to Cm, and I take a regular fiber of that, the fiber is going to be complex, but for now, we only know it's almost complex. An important example of one of these would be a smooth affine variety. It's an example of a manifold. You can think of it as a real manifold, as a submanifold of R2n, and it inherits a complex structure from the ambient Cn. I should say an almost complex structure, which later we'll talk about the fact that it's complex. All right. Any questions? So if we have a manifold and it has a symplectic form and it has an almost complex structure, then we can ask, are they compatible? And that's just the question, are they compatible as a symplectic structure and a complex structure on each individual tangent space? So I take this combination of them I would have before. I take the symplectic form, but before I stick in the second one, I multiply it by this almost complex structure. And I want the thing that comes out of that to be a Riemannian metric. So I want it to be an inner product on every tangent space. So theorem, any symplectic form has a compatible almost complex structure. And basically we just do this operation we talked about before on vector spaces on each tangent space separately, right? So we're going to get an endomorphism of the tangent bundle such that, if we pick any Riemannian metric, we get an endomorphism of the tangent bundle that connects that guy to the symplectic form. And we can do this linear algebra operation that we did before of kind of saying, oh, well, those guys don't quite work out. You again have this weird kind of decomposition into two-dimensional sub-bundles that's going to be compatible, but I can sort of remove the annoying diagonal entries and get to something whose square is -1. All right, so today I will be good and take a break. Justin, are you there?
Yeah.
So if anyone wants to ask questions, Justin will be here. I will be back in a couple of minutes.
Sorry, Ben, one thing.
Yeah.
Are your lecture notes online so I can scroll through them? at the
Yes, of
site?
course. Yes, they're linked on the Notion.
Okay, great. That's all I needed, just so I can know what people are referring to when they ask me questions.
So I have a question which is like sufficiently dumb that I was embarrassed to actually ask it during the lecture, which I think is exactly this is exactly the moment, right?
Yes, that's exactly the moment.
Yeah. Okay. So A star came up, and how exactly are we supposed to think about A star?
Yeah. So give me a second because I have to.
I think what's going on is that because we have a Riemannian metric, given A, we have A star because we can think about the Riemannian metric as identifying the vector space with its dual. And so then we call it A star, the map from V dual to V dual. Well, A induces a map A star from V dual to V dual, and then we're identifying both those V duals with V's, and that's why we write A star still as a map from the same vector space to itself. Is that what's going on?
Yeah, so we have, as you said, we've got these two different forms that both give us an identification of V with V dual. But then you might ask, is there some map that we can use to fill in so you have like two different maps from V to V dual, and then you might ask, is there a map that I can fill in the triangle with?
Yeah, no, I mean,
and that map is A.
Yeah.
Okay, so that's the first map.
So the thing I guess I'm being puzzled by is the notation A star.
Yeah, so let's see. So it's true that A is skew symmetric. Yeah, so I think A star is just is maybe the adjoint.
Okay, can you sorry, it's
yeah, so right, like anytime you have like a Riemannian metric and you have let's see.
Okay, I mean that sounds like
I think you can define a map. I think you can define a map A dual by that equation. the
okay,
G of
okay,
A
so that-
dual V U V is GU of AV.
Okay, so that we can take that as the definition of a dual.
I believe so.
That sounds exactly right. I think that amounts to the same thing as what I was saying, that we want to think of A star, or that A star notationally should be a map from V dual to V dual, but we're identifying the V's and the V duals, but we're using G to do that. I think that should be the same thing as what you just said.
Yeah, let's see.
Yeah, I think that's exactly right.
Okay, good. Yeah, okay, so yeah, I think this G dual is just the adjoint. Yeah, and in particular, the important thing he proved is that that the adjoint is the negative. So like right when he writes that equation, the thing that he immediately uses is he proves that A star is minus A.
Thanks. I should also look at the notes, which I am not currently doing.
I mean, but that's special. That's only because we defined A like using the simplicity, like as the difference between the symmetric form and the alternating form. But like in that particular case, when you've defined an A in that way, the important equation. So it's defined like, you know, as I said, using this equation about G of A dual UV being G of UAV, but then because you know that you have this relation to the symplectic form, you can show that A dual actually has to be minus A.
Right.
I think I even wrote down the proof that A dual.
Yeah,
is
yeah.
minus A. Yeah, there it is.
I mean, like if G was the standard metric, A dual would just be the transpose.
Right, which is another way of saying this is if you pick an orthonormal basis and look at the matrix with respect to that, then it's skew symmetric in the usual sense. Josh?
Yeah, I had, I guess, a sort of naive conceptual question about symplectic forms, which is basically that, you know, we will like to say that it's a symplectic form is essentially an area measurement, right? It's a sort of two-dimensional thing. But the thing is that, I mean, a symplectic form is in dimensions greater than 2 is going to vanish for certain pairs of vectors. So I'm just kind of curious as to, you know, how, to what extent you can really conceive of it in that way.
Well, right. So I wouldn't, it's not exactly an area, right? It's, I mean, or at least you have to be very careful how you interpret it as
Right.
an area. So I mean that's. I mean, it induces a volume on the whole thing, but of course it's more structured than that, right? So I mean, one way to think about it is that, yeah, it's kind of on any two-dimensional subspace, it's giving you some notion of area, but on some of those subspaces, the notion of area is going to be trivial,
Mhm.
right? And so amongst other things, it's telling you that some of those subspaces are special because the area is trivial on them, right? So I don't know, yeah, I'm not sure exactly what to tell you other than that's maybe not the most intuitive way of thinking about it.
Okay.
Vasiliki? Yes, so I think I've missed that part, but what does it take for an almost complex structure to be complex? Does it have to be on a flat space?
No, so we'll talk about this quite a bit more on Wednesday. So I don't think you missed anything.
Okay.
I just wanted to kind of like flag that this is called almost complex. It might seem weird that I put that almost there, but there's an additional condition we want to call it complex. So, I mean, flat isn't the right word, right? But you should think of it as kind of analogous to flatness in Riemannian geometry. So somehow, like,
okay,
if you, or to having a non-degenerate two form, but not including this condition that the symplectic form is closed. So Canis de Silva makes this, and I think it's a good sort of analogy of, you know, if you just put on the notion of the right kind of linear algebra structure on the tangent space without paying any attention to kind of how they relate to each other, you get the notions of Riemannian metric, almost complex structure, and then almost symplectic structure, which is a non-degenerate two form that you don't assume is closed.
mm-hmm.
And then there's an extra condition you can put on them that's sort of which in Riemannian geometry is flatness, in symplectic geometry is being honestly symplectic, having the symplectic form be closed. And in the complex world, well, it's a little complicated to say what the tensor involved is, but it's sort of saying that it looks locally like Cn, right? Being flat as a Riemannian metric means you look locally like Rn. Having your symplectic form be closed by the Darboux theorem means you locally look like T star Rn. So the sort of thing you need to get rid of that almost is that you locally look like Cn.
I see, thank you.
Mm-hmm. No problem. And, you know, like next, the main topic of Wednesday is supposed to be what this deal with complex versus almost complex manifolds is. All right, any other questions? All right. Right, so we covered an almost complex structure that's putting the structure of a complex vector space on every tangent space in a way that's sort of smooth. So this is making the tangent bundle into a complex vector bundle. Another way of saying that. Or reducing structure group from GL2NR to GLNC. Different ways of putting what you're doing. All right, and we can ask about compatibility between almost complex structures and symplectic forms, and we can always find that. Whenever we have a symplectic form, there's a compatible almost complex structure. And there's this notion of a compatible triple, which is a metric, a symplectic form, and an almost complex structure that are related by this formula. So this is just kind of packaging up all the information, right? When you have a compatible symplectic structure, an almost complex form, you will get a metric that's compatible that comes out of it automatically, right? The statement is exactly that this guy on the right-hand side is a metric. So just say, we're going to include that metric as part of the data. So things I will note here, I didn't use that the symplectic form was closed. So this statement is also true for almost symplectic structures. All I ever did was sort of fiber-wise stuff. It's worth noting here, right? So we've shown that if you're given a metric and a symplectic form, you get an almost complex structure. If you have a symplectic form and a compatible almost complex structure, you get a metric. But what about if you have an almost complex structure and a metric? You don't get something symplectic, you get something almost symplectic. So you can do this linear algebra kind of backwards of, use this formula to define omega using omega of uv is equal to gu minus jv. But so that gives a non-degenerate 2 form, but we have no reason to think it's closed. So we get something almost symplectic, but it might be that you have an almost complex structure and there's no way of choosing a metric so that you get an actual symplectic structure instead of just an almost symplectic one. It might be there's no way of choosing a metric that makes this d omega vanish. So kind of in all of these cases, you can ask, is it complex? When you get this metric, you can ask, is it flat? And when you get this almost symplectic form, you can ask, is it symplectic? Does it have d omega equals 0? And kind of nothing about the linear algebra we've done helps you to answer that question. So I'm just kind of flagging that as that question exists and the answer is difficult. And an example of this is that S6 is almost complex, but there's no symplectic form on it, as we saw before. Right? We saw that there's no symplectic form here because the Durand cohomology vanishes in degree 2. And on a compact manifold, a symplectic form has to have non-zero second cohomology class. So there are plenty of almost symplectic structures on S6, but there are no symplectic ones. One more note about these arguments we've used. There's nothing special about the tangent bundle. You can take any vector bundle and define a metric on it, a symplectic form on it, so a symplectic structure pointwise on the fibers of the vector bundle, and similarly an almost complex structure on the vector bundle. On a general vector bundle, I can talk about a metric, inner product on fibers, symplectic form, fibers. And I can also ask about an almost complex structure. structure and fibers. And just as above, I can apply these arguments of any symplectic structure. I should really call this an almost symplectic structure. Any almost symplectic structure gets you an almost complex structure and vice versa, using a metric to pass between them. Every vector bundle has a metric by sort of usual argument using partitions of unity. But there's, I should just say here, there's kind of no obvious generalization of this exterior derivative being zero condition. So all of these guys, it's kind of unclear what it would even mean for a metric on a random vector bundle to be flat, or what it would mean for a symplectic form on the fibers to have d omega equals 0. Oops. Or what it would mean for this to be complex instead of almost complex. So somehow those conditions are something special about tangent bundles, whereas the just kind of underlying linear algebra on each fiber is something you can do on any vector bundle. All right, so one of the kind of underlying themes of all of this is that metrics are somehow very kind of sturdy objects. You can do lots of operations with them, and you're unlikely to screw them up, which, you know, is kind of manifest in this: every manifold has a metric. Yeah, Josh.
Yeah, so you mentioned that it's not clear how to define the notion of flatness for a metric on an arbitrary vector bundle. It's kind of interesting because I know that, like, with say a Riemannian metric, you get this notion of like a connection, which is something that's defined on the tangent bundle that kind of lines up the fibers, so to speak.
You can ask whether a connection on a vector bundle is flat. That's a very good question. Okay. Exactly what's happening is on the tangent bundle, when you have a metric, there's a canonical choice of connection called the Levi-Civita connection, right? So yeah, exactly what's happening here is on an arbitrary vector bundle, there's a notion of flatness for connections, and then for a given metric on the tangent bundle, you get a connection.
Okay.
I don't believe there's any connection between metrics and connections on other vector bundles.
All right. Yeah.
I'm not an expert on this stuff, so maybe someone will tell me I'm wrong. But you know, somehow that's something very specific about connections, or something where you put in tangent vectors. So right, somehow the point is, like, when you are trying to put a connection on a tangent bundle, tangent vectors play two different roles. They're both the actual things in the bundle, and they're the things you're trying to differentiate with respect to in the connection, right? Whereas if you have a general vector bundle, there's no connection between those things, right? Tangent vectors are somewhere, something somewhere out in space, and, well, tangent vectors are really on the manifold, and these fibers are just something else, and there's no connection between them. And so, like, that's kind of the issue.
Okay, thank you.
And I mean, I don't think it's literally the same issue with these other ones, but it's a similar sort of idea that you're really using something special about the tangent bundle when you define the exterior derivative of a two form, and you're using something special about it. We'll talk about the almost complex structure before, but kind of both of those are things you can phrase in terms of the exterior derivative, and that's a special thing about about the tangent bundle. All right, great. Any other questions? Okay, so, this is maybe just me kind of philosophizing, but like I say, metrics, they're somehow these very kind of floppy things, or, well, yeah, I'm maybe not using these words in a very constructive way, but, somehow metric, why do I sometimes call the same thing floppy versus sturdy? And the point is, a metric is something where you have a lot of possibility of deforming it and doing funny things to it. And because being metric is such a nice property that's hard to change, you probably won't change it. This positivity in particular is really useful. Whereas, symplectic forms and complex structures, it's a kind of trickier thing. It's kind of harder to, for example, use partition of unity to take two symplectic forms or two complex structures and try to interpolate between them. It doesn't work. The properties they have to satisfy aren't compatible with that, whereas the ones for metrics are. So it's nice. Kind of another manifestation of this is that a metric induces a metric on any submanifold, right? If you have a subspace of an inner product space, it itself is naturally an inner product space in a totally canonical way. And kind of all subspaces of the same dimension, they're all inner product spaces that kind of all behave the same way. Whereas a symplectic structure or a complex structure won't treat subspaces in the same way. It will kind of distinguish between subspace it likes and subspaces it doesn't. So sort of key here, subspace of inner product space is again inner product. Whereas a subspace of a symplectic vector space well, you can get all kinds of stuff. You could get Lagrangian subspaces. You could be, again, symplectic. You can be neither. Right? You can be isotropic, co-isotropic. There's kind of all these different possibilities for how the subspace plays with the symplectic form, whereas for an inner product, it treats them all the same. And similarly, the complex structure, right? Well, if you have an almost complex structure on a manifold and you pick a random submanifold, it's pretty unlikely that when you hit the tangent space of that submanifold with your J, you get the same guy back, right? Usually that's not going to happen. But sometimes it does. And when it does, we call that submanifold almost complex. So that's what we need for a submanifold of an almost complex structure to have it induced almost complex structure. And most submanifolds, well, just something else wacky happens, right? J sends that tangent space to some other thing. Maybe it's transverse, maybe there's some overlap. You can have all kinds of nasty stuff going on. But because of this kind of triangle property, if your subspace is well behaved with respect to two properties, to two of these guys, then it should be well behaved with respect to the third. And an example of this is if I have an almost complex structure and a compatible symplectic form, then that submanifold is actually symplectic for the symplectic form. It's almost complex, that implies it's symplectic. Unfortunately, the implication doesn't go the other way if you think about it. Right. So it's not true that a symplectic submanifold needs to be almost complex. Somehow this is a slightly stricter property. But it sort of tells you about how these guys kind of play together. And I'll just mention here, actually one of the reasons we're going through this is one of the kind of prime examples of symplectic manifolds is manifolds where the complex structure is much better known. So I mentioned smooth affine varieties, right? we're going to prove that I think those are always symplectic. I don't think you ever have a problem getting the d omega 0 there. I should probably check that before I tell everybody, but I think that's right. And so those will always have a symplectic form. And in fact, I've sort of got part of the argument here, right? That if I look at Cn, that has a symplectic form and a compatible almost complex structure coming from the obvious thing. I don't think I ever actually wrote this out. Maybe it's worth saying. If I take Cn, it's got coordinates zi, which I can write as in terms of real coordinates as xi plus iyi. Then what my compatible almost complex structure is going to do, it's going to send ddxi to ddyI, ddyI to minus dxi. So that defines for me an almost complex structure on Cn, which is sort of the obvious one coming from the actual literal map of manifolds given by I squared. And any submanifold of Cn, which is almost complex, is also going to be symplectic by exactly this argument here. And maybe I'll just add, since we had talked so much about being concerned about staying closed, right? What's the proof here? So need to check that given V in the tangent space to X, that omega V u is not equal to 0 for some u in T star of X. That's what it means to be a symplectic submanifold, that the symplectic form stays non-degenerate. So every tangent vector to the submanifold has non-zero pairing with some other tangent vector. And of course, by tameness, I have that omega of V, J of V is positive, and so in particular is not 0. So U equals J of V works. And you see why I need this almost complex condition. If I had some random submanifold, there'd be no reason to think that J of V would be tangent to it. It needs to be almost complex for this proof to work. And let me just say it out loud because I had been worried about it. So the exterior derivative of omega, I should actually write the pullback. If I look at this pullback, so let I of X be the inclusion of this submanifold. When I pull back omega, that's equal to the pullback of d omega, so it's 0. So indeed, my symplectic form is closed. This is just a general fact about symplectic submanifolds. You don't have to check again that the symplectic form is closed, but since I had made such a big deal about it earlier, I wanted to mention that. All right, any questions? I wanted to mention another one of these kind of consequences of the sturdiness or floppiness, depending on how you think about it, of metrics. And this is actually a really important observation later on in other uses of symplectic geometry, which is that the space of almost complex structures compatible with a given symplectic form is contractible. So a sort of very common maneuver in symplectic geometry is to say, I want to find out something about the symplectic form. I'm going to define this thing I'm looking at using an almost complex structure as kind of an auxiliary thing to do. Well, I had to make a choice there. That's kind of bad. But as long as I show that my choice doesn't change when I deform my almost complex structure a little bit, I'll actually always get the same answer, because not only is the space of almost complex structure connected, it's actually contractible. So I can choose one preferred almost complex structure and give a canonical path from any starting point to that particular almost complex structure. And I think this is also kind of a nice illustration of how useful it is to be able to take this compatible, start with a metric in a symplectic form and find a compatible symplectic, almost complex structure. So I fix my favorite compatible almost complex structure. Could be anyone. I just choose one. It's fine. And I call that J0. And because of the compatibility, this gives me a preferred metric on my space of on my manifold. So, right, whenever I have a compatible symplectic form and almost complex structure, I get a compatible triple, so it includes a metric. Well, similarly, if I have any other compatible complex structure, I get another metric. Oops, this guy. And there's a nice, smooth, and in fact, linear path in the space of metrics between my G0. So the second term here is, this is T times G0 UV. And the metric coming from my other almost complex structure, right? Which is just, I take the weighted average of them, right? And this is sort of the great trick with metrics, is you can always take weighted averages of them and you still get a metric. So in the space of metrics is contractible by exactly this argument that you can always take weighted averages. And so I have this nice path in the space of metrics connecting my two guys. Now, given each metric along that walk, that's not necessarily coming from an almost complex structure fed into omega, but by the argument we gave before, there's a canonical way of getting a compatible almost complex structure out of feeding in omega and that metric. So let me call this HT of J. So this depends on, well, first of all, it depends on my original choice of almost complex structure, J0. It depends on the second complex structure, almost complex structure I put in, J, and it depends on a parameter T that goes between. And so we see how useful it is to have this kind of coordinate-free way of putting in a symplectic form in a metric and getting out an almost complex structure. And again, if I actually use the metric and use the almost complex structure in the symplectic form to get a new metric, it won't be this straight path between my original guys, because there's no reason it should be a compatible triple in between, but it's sort of smoothly deforming away from that straight path, right? So I now get a path in the space of compatible almost complex structures. At 0, it's my original, the one I want to sort of be a variable. At 1, it's this fixed guy I'm trying to contract everything to. And sort of everything that happened is smooth. Everything that happened depends smoothly on the original almost complex structure I put in and the time t. And so that deformation retracts everything down onto this guy J0. All right, are there any questions? So I know this is kind of like everything's happening in this very abstract world. Like you have this whole space of almost complex structures. But I don't know, I think it's a very kind of important thing that, you know, you can kind of, if you prove something using an almost complex structure and you prove it doesn't change when you deform the almost complex structure, you never have to worry about like, oh, well, what if I win around some loop in the space of almost complex structures? Because contractibility exactly tells you you can sort of fill in that whole loop. So even though there are many different almost complex structures, sort of up to topology, they're all the same in some sense, but they really are telling you something very strong about what the symplectic form is, and using them is a very common trick in modern symplectic geometry, which is why we're talking about them pretty close to the beginning of this course. I was a little worried that this lecture would be like, oh God, you're defining more stuff, which, you know, fair enough. But this actually is, it's a very important technique, and it's a very important source of interesting symplectic manifolds, as we'll see over the next couple of weeks. All right, any questions?
Go ahead.
No, go ahead.
Oh, can you say something about what the topology is on this set of of almost complex structures compatible with W omega?
Oh, sure. You know, I should think about what you're correctly complaining that I maybe shouldn't claim that something is contractible before I tell you what the topology on it is. But you know, let's think about what am I actually using here. The kind of important fact I'm using is that this path is continuous. So yeah, let me first say that the kind of slickest way to answer this would be to say, well, actually, maybe I should just assume that my manifold is compact, and I can choose a metric, and then I'll actually be able to put a norm on the space of linear maps from the tangent bundle to itself. And I mean, I think I'm going to say something like, you know, right, what's the topology? So one of the kind of standard tricks so the issue here is that, what do I want a topology on? Well, I want a topology on the almost complex structures. Every almost complex structure is a map from the tangent bundle to itself. So I really want a topology on a linear maps from the tangent bundle to itself. I could also say sections of T star M tensor T of M. So, you know, the fundamental question here is, how do I put a topology on sections of a vector bundle? I think this has come up a few other times, thinking about like forms and such. And I would say the sort of standard answer, so might as well just I shouldn't say standard, random. E over some base. And at least I think the usual answer is pick a metric, pick an inner product. Maybe I'll say family of inner products. Metric a family of inner products. And volume form on B. So this is, I mean, so I'm picking inner products on the actual, oh geez, fibers of E, and I'm going to choose a volume form on my base. And what that allows me to do is it means that if K inside my base is compact, then I can consider the integral over K of the norm of some section. All right. And I can use these as semi-norms on my vector space of sections of my bundle, and that defines a topology. So the sigma such that this integral is less than some epsilon, define an open set. Which is a neighborhood of 0. And if I have a vector space and I'm trying to put a topology on it, the only thing I need to tell you is a basis of the neighborhoods of 0. So for all K, let's give a basis of neighborhoods of 0. All right.
Thanks. I just wanted to make sure that above you, I think, did you mean to write the tensor product of T star M with TM?
Yes, I'm sorry. That got a little messy. Yes, it was a tensor product. I mean, the point is, it's the vector bundle whose fiber at every point is the endomorphisms of the tangent space.
Right.
As a vector space. And I mean, I know I made kind of several auxiliary choices here, but somehow the topology isn't going to depend on them in a very serious way, right? Like if you scale the volume in some funny way, well, you're actually still going to get the same topology. Or scale this metric in some funny way.
And then the claim is that in this topology, the bundle map HT of J depends continuously on omega and GT of J in T.
Essentially, yes, that's what I'm saying.
Like,
well, no, right, omega doesn't change. So there's no question about how it depends on omega.
right, okay.
The question is, how does it depend on metric?
I see, okay.
Right, and all you ever do it, right? Metric is changing continuously. That map A is going to change continuously. So A times A star square root is going to change continuously because everything's positive definite. Worry about square roots doing something weird, and so like that. I think that's basically why those steps are going to depend continuously.
Okay, thank you.
Mm-hmm. So maybe I will stop the recording.